Okay, so this is the second time I tried to record this video. The first time the audio didn't work, so I've got my fingers crossed. All right, so we are going to, right now, we're going to continue on with our discussion of the nature of charge. And we are going to first review what we know already, and then we'll see what we need to do to take the next step so that we can understand it a little bit better. So we're going to review from kind of the very beginning, which is how did people learn about objects? What types of observations could they make that would give them information about them? So here's some object. It has a size, it has mass, has color, has hardness, has density, has brittleness. I mean, there are all sorts of quantities that were observable. But then it turns out that there's this one other, which is called charge, and it is not related to size, mass, color, hardness. It's a completely separate quantity. But by playing around, if you will, which you guys have done some in class already, people have determined that there are two types of charge, and that similar charges repel one another, opposite charges attract one another. And as you know, we now call these charges positive and negative charges, and in our equations, we give them positive and negative values. And we'll review why that is in just a minute, because we have learned from Coulomb, who did the experiment with the torsion balance that we looked at in class last time. We learned from Coulomb that these charges, even though they're invisible, they will exert forces on one another. And the force is proportional to the magnitude of one charge times as a matter of fact, let me not even say magnitude. It's proportional to the amount of one charge and the amount of the other charge, which can be positive or negative, the amount of charge divided by the distance separating them squared, or divided by the square of the distance separating them. And we know that this expression for Coulomb's law is in fact not really entirely correct, because it's a vector force and therefore it must be a vector equation. So what do we have? We have the force on charge 2 from charge 1 is equal to some constant times charge 1 times charge 2 divided by the square of the distance between them. And we know that it is exerted in the direction from charge 1 to charge 2, which here is R12 hat. Okay, but this created a problem. It's created a problem because how does this charge Q1 know how it should be pushing charge Q2? How does it know what direction to be pushing it? Or what if Q2 was over here? How does charge Q1 know now, oh, I'm not going to push off to the right, I'm going to push up and off to the right a little bit? How does it know that? And the only way you can there are two ways to think of that. One way is that this charge Q1 acts differently depending upon where Q2s show up around it. But it's a little bit more reasonable to say, you know what, Q1 is the same whether there's a Q2 there or not. So Q1 has some property, and that property, if we can see that property, if we bring a Q2 close to Q1, we can see that Q1 will exert a force on Q2. But even if Q2 was not there and there was no force being exerted, Q1 is doing something. And that something is something that we call the electric field. And so the electric field is a property of charge, just like charge itself is the property. Charge does not exist without an electric field. Electric field does not exist without charge. So they're just kind of two different aspects of the exact same thing. So it's kind of like saying, a banana is yellow. So yellow is the color of that banana, but you can't have the yellow without the banana. I mean, I know you can have other things that are colored yellow, but you can't separate out the yellow of a banana from the banana. So that's kind of what it's like. So what is this electric field? Well, this electric field, for now, we're just going to say it's something that goes either pointing out from Q1 or pointing into Q1, but these are the directions of the vectors here. So it's pointing in one of those directions. It's pointing in this direction, either positive or negative. So this is what it's like. And not only is it pointing in this direction around Q1, but it really goes to the ends of the universe. So this electric field from Q1 goes from Q1 everywhere. Now it ends up that's a little more complicated than that, but for our purposes now, we'll just say that that is true. Even if it is true, however, you should be able to think about that d squared that's in the denominator of the force, and you should recognize that even if this electric field goes to the ends of the universe, the effect it has is going to be pretty darn weak as you double the distance. As you double the distance every time, the effect of that force is 1/4 as strong as it was before. So it doesn't take long before it gets very, very weak. All right, so what is this electric field? Well, let's just make it easy on ourselves and say this property of Q1, this electric field, let's just say that we're going to define it as the quantity by which we can multiply Q2, some other charge we bring in this area. If we bring a Q2 in and we multiply this the electric field by Q2, we will get the force on charge 2 from charge 1. So, mathematically, it just says that the force on charge 2 from charge 1 is equal to Q2 times E1. This quantity we're just calling E1. And notice the vector signs there. And we'll get to that in just a second. So, how do we figure out then what this E1 is? Well, we already have an expression for F21 from Coulomb's law. So we now have two expressions for F21. That is, we have two expressions for the force of charge 1 on charge 2. And we can just set them equal. And when we set them equal, we get this expression. And you will notice that the Q2 E1 on the left-hand side matches on the right-hand side. There is a K Q1 over R12 squared R12 hat times Q2. So we can just divide those Q2s out and we end up with an expression for the electric field of charge 1. So this is the expression for the electric field of a point charge. That is a charge that takes up no space. Now, there are a lot of times where we can kind of assume a charge takes up no space, even though it really does take up some space. And we'll actually have some of those examples that when we work through our problems. But this right here, this expression, is at the foundation of allowing us to calculate the electric field for any arbitrary charge distribution. Because if we know what it is for one point, you guys already know that if we have some charge out here, and we've got a charge here, 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 we know that the net force on this charge is just the sum of all the individual forces. Well, if it's the sum of the individual forces, and we now have this thing that's called an electric field, we know that the electric field at any point is going to be the sum of the electric field from all of those individual points. And so, what's that going to allow us to do? It's going to allow us to do some calculations for complex charge distributions and determine what the electric field must be. And that's what we're going to work on with the next video.